Hello students, I am Mr. Adinath D Badar, Assistant Professor, Department of Chemistry, Lit Pushpa Devi Patil, Arts and Science College, Resort, Distwashi. Today in this video we are going to discuss topic for B.Sc first year, that is periodic properties. So firstly we see the basic points or contents or fine points of this unit. So first point is basic of periodic table and classification of elements. Next, the second point is atomic radii, its types and trends, that is variations of atomic and ionic radii. Then the next point is ionization energy, its types and trend, electron affinity, its types and trend, electronegativity, its types and trend, metallic and non-metallic characters of elements, oxidizing and reducing power of elements. These are the contents of unit first, part A. So we discuss periodic classification of elements or modern periodic law or modern periodic table, also called extended or long form of periodic table. So we see the statement of modern periodic law, which state that the properties of the elements are a periodic function of their atomic number, or we can simply call if the elements are arranged in the increasing order of atomic number after certain intervals, there will be repetition of properties of the elements, or also the elements falling in a same group shows similar properties. Now these are the main features. The elements are classified or arranged on the basis of more fundamental properties of atom, that is atomic number. There are in all 16 vertical columns. There are in all 7 horizontal rows are also called period. So these are a modern periodic table having 112 known elements. So these are the 16 vertical columns like 1, 2, 3, 4, 5, 6, 7. These are 8, 9, 10, 11, 12, 13, 14, 15 and 16, and these are the 7 horizontal rows like 1, 2, 3, 4, 5, 6, 7. The first row consists of only two elements, from hydrogen to helium. The second period starts from lithium and ends at neon, having or included 8 elements. Like third period also start from sodium and ended at argon and included only 8 elements. Then the first 3 rows are called short row. After that, the row number 4th start from potassium and ended at krypton. The 5th row starting from rubidium and ending at xenon. The 6th group are also starting from cesium and ended at radon and consist of 62 elements, and this is known as long period. The seventh row starting from francium and ended at dubinium, and it is called as incomplete row. Now these are the some applications of long form of periodic table or modern periodic table. The elements are classified or arranged on the basis of more fundamental properties of atom, that is atomic number, by taking atomic number as the basic for classification of elements. The second application is all elements having in the same group have similar electronic configuration as well as similar chemical properties. Then third application is the slight change in properties of the elements which increases in their atomic number from left to right. The transition elements have properties intermediate in between S and P block element, so logically placed in the middle section of periodic table. The elements can be divided into S, P and D and F orbitals or block elements. The elements can be divided into four types on the basis of nature of atomic orbitals, which the last electrons, also called the differentiating electrons, enters. Accordingly, we have S, P, D, S, P, D and F block elements. This classification is also known as differentiating electron classification. Here these elements are called S block elements, and the last or differentiating electron goes in S orbital. Here the center part, that is D block. Here the last electron enters in D orbit, then it is called D block elements. Here P block elements, the last or differentiating electrons enters in P orbital, then it is called P block elements. At bottom these are lanthanide and actinide. The last electrons enters in F orbital, then it is classified as F block elements. On the basis of metallic nature, elements are further classified into three types, that is metals, metalloids and non-metal. The yellow portion shows metals. The blue, these elements are metalloids, that is dual nature, some character of metal and some characters of non-metals. And these are green are non-metal. Now we start the first properties of the elements, that is atomic radii. So firstly we see the definition of atomic radii. So the bonding atomic radius is defined as 1/2 of the distance between covalently bonded nuclei, or simply we can say distance between the nucleus and the outermost shell of electrons of an atom or ion. For example, here these are two nuclei bonded through covalent bond. These are the total internuclear distance d. So bonding atomic radius is equal to 1/2 d, that is the distance from nucleus to the valence shell electron. Here these are atomic state free from ion, and these are ionic radii. If the distance is measured in ionic state, then it is called as ionic radii. If the distance is measured in atomic state or without charge, then it is called as atomic radii. Here these are the nucleus and these are the valence shell electron. So simply it is the distance between nucleus and the outermost shell of electron of an atom or ion, that is simply in ionic state or atomic state. Atomic state, that is free from charge, and ionic state, that is or having a charge. It may be cationic or anionic. So next is the covalent radius. So simply covalent radius can be defined as the half of the internuclear distance between two identical adjacent atoms by covalent bond. Here the diagram shows these are one atom and these are the also another atom bonded through covalent bond. These are the total covalent radius from this nucleus to the another atom nucleus. So covalent radius is equal to half of the internuclear distance between two identical atoms attached by covalent bond. Now, next is the periodic variation of atomic or ionic radii, or simply trend. So, as we move from left to right, like hydrogen to helium, the size of atom tend to decrease across the period. Means simply left to right, size will be decreases as we move from top to bottom, like hydrogen to cesium. The size of atom tends to increase down as a column in a period, that is left to right. There is decrease in the values of atomic and ionic radii with increase in atomic number from left to right in a period. Consider the atomic covalent radii of group second period. It is observed that the atomic radii go on decreasing from lithium to fluorine. Here these are the atomic size. This bubble shows atomic size. Lithium are bigger to that of fluorine. This size is decreases from lithium to fluorine. Generally, the elements that are present to the extreme left, that is alkali metals, left side means hydrogen side, at shows a largest values of atomic and ionic radii, whereas those are present at right side, that is p block elements or halogen family, shows a smaller atomic or ionic radii. However, the zero group, that is noble gas elements, completely filled outermost shell, and these are stable, and this shows a higher atomic or atomic radii. As we proceed from left to right in a period, electrons are added to the orbitals of same main shell. Therefore, distance between outermost electrons and the nucleus remain almost unaffected by the addition of electron at every new elements from left to right, but at the same time there is increase in positive charge, that is a nuclear charge, due to increases in atomic number. This increase in nuclear charge attract the electron more strongly towards the nucleus. The resultant effect is that outermost electron experience more and more attractive force towards the nucleus with increase in atomic number, and hence the decrease in atomic and ionic radii. For example, here the hydrogen having one electron in valence shell and one proton in nucleus as compared to helium. Here the extra electron are added in a valence shell of helium. That's why the nuclear charge is increases. So from left to right the nuclear charge is increases. As result, atomic or ionic radii will be decreases. Like same in a group, that is top to bottom. When we proceed from top to bottom, the atomic or ionic radii both increases with increase in atomic number. Like if we consider the atomic or co-ionic radii of second group or alkaline earth elements, it follows that the ionic radii of this element go on increasing from beryllium to barium. As we like here, these are the beryllium and these are barium. The size is increases from top to bottom. As we move from top to bottom in group, the following two factors, mainly two factors affected the increase in atomic or ionic radii. So first factor is very simple, that is addition of extra cell at every successive period. When we proceed from top to bottom in group, every time the electron are added to the higher cell which are considerable away from the nucleus. This decrease in electrostatic attraction between nucleus and valence shell electron. Due to this reason, the electron experience a lesser attractive force and hence atomic and ionic radii are increases. For example, in the hydrogen there is only one cell, that is n is equal to 1. Here in that lithium the number of cell is 2, that is principal quantum number is equal to 2, means number of cell is 2, here 3, here 4, here 5, here 6. That's why as we move from top to bottom, the number of cell is increases and the added electron goes away from the nucleus. As result, lesser attraction between nucleus and the valence shell electron. The second factor is the nuclear charge, that is atomic number, increases as we move from top to bottom. This increased nuclear charge causes decrease in atomic or ionic radii due to greater force of attraction exerted on valence shell electron by the nucleus. Out of the two factors, that is addition of extra cell and nuclear charge, out of the above two effects, the first effect, that is decrease electrostatic attraction between nucleus and valence shell electrons due to considerable increases in the distance between outermost main cell and nucleus, play an dominant role and laser the effect of increasing nuclear charge. As a result, we see that atomic and ionic radii go on increasing from top to bottom in a group. Here, these are the example in a period, that is left to right, lithium to fluorine. Here the effective nuclear charge is increases. Here for example in lithium the effective nuclear charge is +1 as compared to fluorine. Here effective nuclear charge is 7. That's why left to right size is decreases as move from left to right. Here lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. The extra electron were added in a same cell. Another here across a group, that is top to bottom. When we proceed from top to bottom in a group, the atomic and ionic radius increases with increasing atomic number due to addition of extra cell. For example, in lithium there are only 2 cells, as compare cesium there are 6 number of cells. So the added electron goes away from the nucleus. Now the last portion of atomic radii is that metallic radius. So definition, metallic radius can be defined as half the distance between the nuclei of two adjacent metal atoms in a metallic close packed crystal lattices. For example, simple R0, that is metallic radius, is equal to internuclear distance between two adjacent metal atoms divided by 2. Here one example, the metallic radius of sodium. These are the sodium molecule. These are the half internuclear distance between two adjacent metal atom. Thank you for watching this video. In next video we will see ionization energy and electron affinity. Thank you.